Hello everyone, in this video we are going to do some calculus in polar coordinates. So before we can talk about slope, we want to be able to graph this function. This is a good little bit of review. So we want to look at r is 1 plus cosine theta. So we just plug in our little table here, right? So when theta is 0, we add 1, we get 2. At pi over 4, we're going to get 1 plus root 2 over 2. At pi over 2, cosine is 0, so we just get 1. Here, I'll put in these nice polar coordinates, so I'll mark the points so far. So this is 2, 0, and then 1 plus root 2 over 2 is around 1.7, so, something out here. Then we go to 1. At 3 pi over 4, we have cosine is negative there, right? So this is 1 minus root 2 over 2. And therefore going to be something like the 0.3-ish range down here. And when we get to pi, we get 0, right? And then it's going to reflect because of symmetry, and so we know this ends up looking something like this. Okay, so we're going to look for slope. Now, one thing that we might try here, right, so if we think of r as f of theta is just to take r prime, right? Take f prime of theta. Well, this would be equal to just negative sine theta here. So does this give us slope, right? This is a reasonable guess. Well, what's an easy point to check? So at theta equals 0, we should have vertical tangent line, right? But sine of 0 is 0, so this f prime of theta is 0 here. That would suggest a horizontal tangent line, so no, that's not going to do it. So what do we want to do? So we actually want to do something similar to what we did with parametric equations. So, right, dy d theta is dy dx times dx d theta by the chain rule. And if we want to find dy dx, which is the slope that we would like, right, so we're still in the xy plane, it's just that, our grid is different. We're thinking in the r theta terms. We still want to talk about slope this way, and so in this case it's going to be dy d theta over dx d theta. Well, that takes a little bit more work because we know what? We know y is r sine theta, and r, remember, is like our f of theta. I'm going to do this in general first before we look at that example. So you want to think of this as f of theta sine of theta, and x is then f of theta, or r, cosine theta. So when I take the derivatives of these, I have to do the product rule, and we end up getting this. So in general, this just requires some plugging stuff in, right? So this is the formula for slope given theta. So let's look at an example. Okay, so we're going to look at the one we had previously. So r is 1 plus cosine theta, or we can think of this again as f of theta. So my f prime of theta is negative sine theta. And so plugging things in, we end up getting this. So what I want to know is, where are my vertical tangent lines? So in that case, I should be looking for values where the bottom is 0 and the top is not 0, right? So we're going to rewrite this in a nice way. So notice at the bottom we can factor out a negative sine theta and collect our 2 cosine thetas there, and we get 1 plus 2 cosine theta. And we set this guy equal to 0. So when is this going to be 0? Well, it's two cases, right? So either the sine of theta is 0 or the 1 plus 2 cosine theta is 0. If sine of theta is 0, well, that's going to be at 0 or pi. And here we're looking for cosine of theta is negative 1/2. And if you feel confident about your unit circle, that means theta is 2 pi over 3 or 4 pi over 3. Now, if we look back at our picture, right, so I'm not going to redraw the whole thing, but it looks something like this. It looks like we have 3 points with vertical tangent lines and not 4. So why? Well, remember, we also want our numerator to be non-zero. And at theta equals pi, well, what happens? So sine of pi is 0, we have cosine of theta, or cosine of pi, is -1, and then cosine squared is 1, and so those cancel out. So basically, this guy is gone, and we see theta equals 0. This is 2 pi over 3, and then this guy is 4 pi over 3. All right, so for your first exercise, I want you to consider the function f of theta equals 2 sine theta. You should graph this, by the way, and you should be paying careful attention to how far you need to go with theta in order to trace out the whole curve. So then I want you to find dy dx first, and then, again, thinking about my previous statement, find the unique r theta coordinates where there is a horizontal tangent line. So the next thing we're going to talk about is area, right? So to compute area under a curve, we use the definite integral, right? And we used Riemann sums to define that in rectangular coordinates. So we're going to do something similar here in polar coordinates, although, again, rectangular coordinates, it made sense that we used rectangles. Here, we're going to be using sectors. So what do I mean by that? So if you just consider a circle of radius r, how much area is there? There's 2 pi r, right? Now, what if I just squeeze out a little sector here where my central angle is theta, right? So I just have this little piece where my angle is theta and my radius is r. How much area is in that? Well, if the whole thing is 2 pi, then theta gives us 1 over 2 pi over theta of our circle, right? Why? Because, well, 2 pi over theta times theta is going to give us 2 pi. So, right, 2 pi over theta, pieces of this put together gives you the whole thing. Well, why does this matter? What's my point? Well, we know the whole thing has area pi r squared. Well, if we divide it by 2 pi over theta, we're going to get pi r squared theta divided by 2 pi. My pi's cancel, and I get 1/2 r squared theta. So this is exactly the area of a sector with angle theta. Okay? So now we're going to be able to use that. So what's the whole point here? So let's say we have some curve in our polar coordinates, and I want to know how much area is in this region here, right? So this is, say, from theta equals alpha to theta equals beta, right? Fixing a theta is going to give us a straight line, and then we take all of these r values between, right? So if I want to figure out this shaded area, well, I'm going to do the Riemann sum thing, except for I don't have a way to easily define rectangles, but I can break this into sectors, right? And then these sectors can be at least somewhat accurate in approximating our area. And obviously, the more sectors you take in between, the better your approximation is going to be. And in general, we're going to be using this formula, the 1/2 r squared theta, to get each of our sectors, except for what's happening. Our angle is going to 0, right? You can think of this gap here as our delta theta, and so we're basically shrinking that as we take more and more thinner and thinner sectors. So what starts out is looking something like a sum from 1 to n of 1/2, plug in your test points, column ci squared delta theta. This turns into the integral from, well, theta equals alpha to theta equals beta of f of theta squared d theta, or, since r is equal to f of theta, 1/2 the integral from alpha to beta of r squared d theta. So this is going to be the area under r equals f of theta from theta equals alpha to theta equals beta. All right, so for our one example that we're going to look at here, we're looking at r equals cosine of 2 theta. So if you trace this out, you end up getting this flower type thing, or like you have rose petals. And so what I want to ask is, what is the area of one petal? So you have to figure out what angles actually make one. And so for instance, this bottom one here is from theta equals pi over 4 to theta equals 3 pi over 4 that traces this out. So if I want to figure out my area, well, my area is going to be equal to 1/2, right? I'm going from pi over 4 to 3 pi over 4 of my r squared, so cosine squared of 2 theta d theta. So we've seen integrals like this before, right? So we should be using the trig identity cosine squared x is 1/2 times 1 plus cosine of 2x, where here x is equal to 2 theta, so we're going to get a 4 theta in there, and that's why I used x, right? So this becomes 1/2 times another 1/2, so we've got 1/4 integral from pi over 4 to 3 pi over 4 of 1 plus cosine of 4 theta d theta. And then we can integrate, right? So we get 1/4 theta plus, well, here when we do the u substitution, we're going to get 1/16 sine of 4 theta from pi over 4 to 3 pi over 4. All right, well, 1/4 times 3 pi over 4 is going to be 3 pi over 16 plus, well, sine of 3 pi is 0, so that's going to be 0, minus, we're going to have just pi over 16, again, plus 0, because sine of pi is also 0. So we get 3 pi over 16 minus pi over 16, that's 2 pi over 16, or pi over 8. All right, and there's no second exercise, so thank you for watching.